Welcome to a new episode for the Rootly AI Labs. I am Sylvain Kalash. I am the head of the Rootly AI Labs. Today we are joined by Lawrence, a fellow at the Rootly AI Labs who pioneered this benchmark. Welcome, Lawrence.
Thanks, Sylvain, for having me. Super excited to be here today and show what we got.
Lawrence, can you tell us what's new about Llama 4?
Absolutely. To give some quick context for those who might not be familiar with Llama, Llama is a family of open source language models developed by Meta. And just recently, Facebook Meta released Llama 4, which is the latest generation of Llama models. What makes Llama 4 different from its predecessors is its training technique. Llama 4 has a 2 trillion parameter teacher model known as the Llama Behemoth. It's this giant teacher model that uses something called distillation to transfer the knowledge of its large Behemoth model into smaller models, the Llama Scout, Llama 4 Scout, and the Llama 4 Maverick, both of which are MOE or extra expert models.
Right. So this MOE stands for Mixture of Expert Architecture. And it's really interesting because it's supposed to enhance the efficiency by activating basically only relevant parameters necessary for a specific tasks. So with conventional model, where multiple models collectively predict outcome, here MOE use like a network of these experts and will basically only call the ones that are interesting. Lawrence, can you brief us at a high level on how did you put together this benchmark?
I think the biggest question we wanted to answer is how can we determine the robustness or the efficiency of a model when it comes to solving a software reliability task. So the idea was it's hard to simulate something because there's so many moving parts. So we wanted to do something that was simple to set up and simple for people to reproduce. So we ended up developing the GMCQ, or the GitHub Multiple Choice Question Benchmark. How it works is you give the model a single prompt, which is actually a real world GitHub issue. The issue has to be a bug. And we then show it 4 different pull requests. One of them is the correct pull request. 3 of them are incorrect pull requests. And model has to choose with very limited context based on the current issue, what was the actual GitHub pull request that closed this bug issue. So that it really is the intuition behind the GMCQ benchmark.
Very cool. And we source this issue from the Mastodon GitHub repository. So, we know these are like real world like situation. So findings, which perhaps is, the most interesting or among the most interesting part of this conversation. We were not able to reproduce Meta's finding on Llama outperforming GPT-4o, Gemini 2.0 Flash, and DeepSeek version 3.1, which is the new version. That's how they mention it in their benchmark. It actually came last in accuracy, and I will share my screen here. As you can see, it ranked last. We use Maverick, which is mentioned in Meta's finding as the best performing one for coding, and also the one that is the most able to achieve complicated tasks. So coding is definitely one of them. As you can see, GPT-4o and Gemini 2.0 Flash are by far better. If I'm looking at the actual result, the top one, let's see, they achieved an accuracy of, I think it was 82%. The Llama was only at 70%. So it was at 88% actually for both of the top models. Then we compared Llama 4 against a model that are specialized in coding tasks. I think at this point, it's unsurprising that if they cannot, the first type of model I show were kind of classic multimodal ones, which are not specifically designed for coding. So when we compare this to coding one, obviously we were not expecting the Llama 4 family to perform well. But as you can see, O3 Mini and Gwen Coder perform very well with 90% accuracy. And actually what's quite interesting is that Llama 3 performed better than the Llama 4 family, at least on our benchmark, right? Again, that's our finding with the data set and methodology that we used. So now, because everything we do at the AI Labs is open source, you can actually reproduce this and try to replicate the findings. Lawrence, can you walk us through how did you go about, like more detail about the data set, and how did you go about creating a data set that could be used as a benchmark and show people how they can get started on using it?
I'll start by talking about how we created the benchmark, and I'll eventually kind of move towards how we ran the evaluation part of it. I guess to make it more visual, I'll also share my screen on my side just to give a bit of a visual of how things worked out. So this is the Mastodon GitHub repository, and essentially Mastodon, for those who might not be aware, is an open source social networking platform. And essentially on Mastodon, if you go to the issues part, there are essentially many issues, anything from bugs to documentation recommendations to everything in between. And in our case, we were specifically interested in bugs. So you can actually go on GitHub and filter for bugs. And evidently, there's a lot of fixes that happened both recently and from some time ago. And for many of these bug fixes, you can actually identify whether the pull requests or what are the changes in the code that actually solved and closed the issue. So in many cases, for instance, you can like go in here, you can actually look at the real actual code, look at the actual lines of code that changed, that solved the issue. And what we did was we used the GitHub Python implementation of the GitHub API to actually query through a subset of the bug issues, and subsequently figured out what were the changes in lines of code associated to each issue and each pull request. So that's what we did for the data curation. And you can actually access this directly on our GMCQ repository on the Rootly AI Labs. You just go to Rootly AI Labs and you look at the GMCQ benchmark repository. And we nicely compiled all of our data under here into the data folder. So this is our initial version, our initial release. And there is this JSON-L file which you can download. Similarly, if you go to configs, there is a file that looks something like this, and YAML. And the reason why we have these two files is these are the two files that you would need to download in order to run this on OpenAI evals. So to give you some context on what OpenAI evals is, OpenAI evals is a library that OpenAI developed in order to benchmark their language models. And we wanted to be as industry standard as possible. So we decided to basically reuse the OpenAI evals package to do our own evaluations as well. So in our case, in order to implement our GMCQ benchmark, there's two files that we needed to upload. And we'll show you very quickly how we did it on our side. So there was one file, which was the JSON-L files. The JSON-L file itself is the actual data. So if you go into the OpenAI evals repository, if you go to evals, registry, data, you have all these folders. And in our case, we have a folder specifically for the GMCQ. So over here, we call it the Rootly SRE MCQ mini, and the JSON-L file is uploaded in this folder. So this is something that you can do at home. You can fork the OpenAI evals repository, and you can upload the JSON-L file from the Rootly GitHub repository to your OpenAI evals fork. This is the first file. The second file involves going to registry, evals, and you upload your file over here as well. So in this case, we have the same YAML file that we had on the repository. And this basically is all you need. You just need to upload these two files in order to get our GMCQ benchmark nicely uploaded on OpenAI evals. How it works is you would just run the following command after you start it. In our case, we specified we only want to evaluate a single thread at a time to prevent rate limiting. You use the OAI eval command in the terminal or the command line. And then in our case, we actually implemented multiple models, model endpoints, which you can also do based on the OpenAI evals documentation. So in this case, we're evaluating Llama 3.3 using Grok as an inference provider. And then we specify the name of the task at the end. So press enter, and often within minutes, this is all you need to run these evals, which we then use to benchmark our code. So yeah, that was a brief work through, and super excited to hear this recommendations or the feedback you have, and happy to have a further conversation on other people's findings.
So because we are testing a different type of model, can you speak about the different ways that we tested these models, the different providers for the models?
Absolutely. So a lot of these models are quite large. You have things that might be on the 32 billion parameter byte, the 70 billion parameter byte, which makes it not quite easy to run 7-8 different models at the same time. So we use what we call inference providers, basically providers that already host your models and allow developers to quickly call them in a very cost-effective manner. So in our case, we used Grok and Together AI, two inference providers for a variety of open source models. And we also used OpenAI as an inference provider and Anthropic as well for OpenAI models, Anthropic models, and also Google as well for the Gemini model.
Super. Yeah, and we thanks Anthropic for their support in supporting the labs and providing credits for us. So as we can see, testing a model takes a bit of time. We may get to this screen after, as Lawrence said, everything we build is shared on GitHub. You are welcome to clone the repo and try it on your own. Also, the ways that prompt can make a difference. So also if you want to play with it, go for it. You can reach out to us via email or on GitHub. You can do pull requests. We accept them. I mean, at the end of the day, it was fairly clear that Llama 4 didn't perform well on coding tasks. That being said, we only benchmark this on one type of task, which is by no means the full representation of what a model can do. We are looking at adding additional tasks and also making them open source. If you have ideas of tasks that we believe we should implement, please let us know. The only requirement is that everything we do is open source. So if the dataset is yours and you don't want to open source it, we probably won't be able to use it. But if the dataset that you want us to use is open source, or you are willing to open source your data, then we'd be happy to use it. So we can see here we have the result of this specific benchmark task.
Yep. So we have 70.7% accuracy with a 5% standard deviation. And I think the useful thing to know is that when you're evaluating on a data set that's still relatively small, you might expect some variations between one test to another. So usually these variations are within the standard deviation. So you would expect maybe a few percentage points difference, which is normal. However, if a model is scoring, let's say 50% and another model is scoring 90% with a standard deviation of 5, then you can very confidently say that one model is performing better than the other. If you have models that are very, very close to each other with a relatively noticeable standard deviation, it's normal. These models might switch results. So it's definitely something to watch out for. But as we increase our data set size in future model releases, there's a good chance that the standard deviation will go down, which will definitely be able to improve the confidence of ranking models that are very, very close to each other. But if models are very far apart, with our current setup, we can very confidently tell if two models are very far apart, which one performs better than the other.
Super. Thank you, Lawrence. All right, that's it for today. Here is all we got for this project. Again, we are working on building more tasks, and we'll share the findings with you guys. If you are interested in contributing in some shape or form to the Rooty AI Lab, please let us know. We are always looking to onboard new fellows and partners. Thanks for listening.